Yeah, good morning. Also from my side, I would like to give you a brief update on the status of the satellite gravity infrastructure, which we consider, of course, also as part of the GGOS infrastructure. To do it. It's not yet. Full screen. Yeah, okay. Maybe. No, okay. If I can do it, yeah, no. Here, but not on the. Maybe you did not share it. Oh. Yeah, this is good. So thanks. Sorry. Yeah, this is more or less the time schedule. And I have to say, I will mainly concentrate on the activities on US and ESA side. We know that there is also a Chinese gravity mission in orbit, but community doesn't have any information on this. So I will concentrate maybe on the progress of US and ESA basically. And you know that we have now a very valuable time series since 2002 from GRACE and GRACE Follow On. GRACE Follow On is still healthy. Also, we are partly doing it based on redundant units. So there is some risk that this will not continue very long. And therefore, since 10, 15 years, we're already talking about continuation of this time series of mass change. And the current idea is to even extend this in terms of a constellation, meaning instead of a single pair mission where we measure the intersatellite range, as we do it in GRACE and GRACE Follow On, we would like to launch 2 pairs to increase spatial and temporal resolution and also reduce significant errors, which I can show you later. So what is the motivation for this? With these temporal gravity missions, we have a unique chance to monitor directly mass changes. So with gravity, we are directly sensitive to mass and mass changes. And beyond geodesy, which of course is also our interest to get time variable gravity field, we didn't really talk yet about, let's say, the time component of the international height reference frame, but at some point we have to do it because we know we have stations where we have a vertical motion of a centimeter per year. And of course, just if you want to compute good orbits, then we need time variable gravity field information because these are important disturbing forces for orbits. But let's say that the main selling point is, of course, not geodesies, but it's geoscience applications. And the main selling point for these type of missions is definitely getting a better understanding of the global water cycle and how is water redistributed in the Earth system. Also about droughts, floods, and other extreme water events. And one of the driving factors that I mentioned here explicitly, because we had the similar discussion yesterday, is this essential climate variables. And we can show that we can contribute with temporal gravity to many of these essential climate variables. And I would like really to emphasize that they are really ranked very high, that the programs at ESA are structured according to this, meaning if you want to have a new mission in this field, you have to justify, okay, I can contribute more or less directly to this and that ECB. So big funding programs in ESA, such as, for example, the climate change initiative, are directly linked to this, just to demonstrate the high level, the quasi-standard, these essential climate variables have achieved in the community. And that the target would be to follow a little bit, at least in geodesy. And the good news here already is that we achieved to get the terrestrial water storage, which is more or less the direct observable of GRACE and GRACE type missions, as a new essential climate variable in 2022 GGOS strategy plan. And based on this, we achieved also an IGG resolution in Berlin 2023 on a sustained terrestrial water storage monitoring by dedicated gravity satellite constellations. Also giving this initiative a push from the community. Well, the current status is, as I mentioned it, that we are planning for this double pair concept. And the additional pair beyond the follow-on of Grace follow-on, so to say, is currently still called, not a very nice name, NGGM, Next Generation Gravity Mission, which shall be a similar satellite pair as Grace, or Grace follow-on, but in an inclined orbit. And from this, we expect a much enhanced spatial and temporal resolution, reduced uncertainties and latencies, and we would like to demonstrate operational capabilities. And this is, especially from European side, very, very important to demonstrate that at some point we can really contribute to operational services, for example, in Copernicus. And the medium-term goal would be that this mission is a demonstrator mission to get at some point into the European observation Earth observation program, the Copernicus Sentinel program, as a specific Sentinel observation line, meaning that we make gravity observation from space operational, as we were successful to do already, for example, for altimetry and meanwhile also ice altimetry. And this would be really a big step to make sure, and from the GGOS perspective, gravity missions are always the weakest link, basically, because we have practically no redundancy. Meaning if Grace follow-on fails, then we have nothing in orbit for monitoring of temporal gravity. And therefore, it would be important to set up a sustained system for this. And on top, we have now this magic, and magic is then this, let's say, virtual constellation consisting of these two pairs. So there is already agreement, and this is already in the implementation phase, the first pair, which is now called Grace C. This is again a NASA German cooperation. It's funded, and the launch date of this will be December 28th is the current schedule. And we would like to follow with the ESA pair, the inclined pair, in 2032, so 4 years later, to have at least 4 to 5 years overlap between these missions and can really make benefit of the corresponding advantages. So to summarize, this Grace follow-on, which is called Grace C, shall ensure continuity so that we don't stop with the mass change time series on the one hand, and due to the polar orbit, we will get global coverage. With NGGM, we'll get enhanced sensitivity, better products, better accuracies, better spatial temporal resolution, and we really would like to demonstrate here with specific choices of the orbit that we can produce with very short latencies products, drought monitoring, flood monitoring, water management applications, and others, which can really be used by operational services. So then in the next step, we could implement this as part of Copernicus. Yeah, I think this is more or less what is written here. And as I mentioned here, what you see here, for example, is the advance we can get with this. So this is currently red is usually bad, so higher errors for the polar pair, so for Grace follow-on. Just with the inclined pair, we alone get significant improvements, and these two pairs working together is then, of course, especially important for these short-term products where we need more data in shorter time periods. Just as one simple example of the advance and also the way towards operational services, what we did here in a simulation study is to investigate what is the impact regarding wet extremes. And we could clearly show that with this expanded, enhanced concept, we are able to detect true extremes in a better way, and also to minimize the detection of false positives. So the whole business is always, you identify, okay, there is risk for a drought, risk for a flood, and the one is that you, on the one hand, you pick it, and the other one is not to give a false alarm. And we can definitely show that we can do much, much more with such a double clear constellation that we are currently doing with GRACE. There are some first initiatives for using GRACE and GRACE follow-on data in operational services, but currently this is still limited due to the limitations of the single polar pair. Yeah, we did in the past years several studies also for ESA to investigate the optimal design of this double pair constellation, also to evaluate what would be the science return, the science output of this. And we are continuing this now by setting up with an extended consortium, European consortium, the crowd processing facility. So it's officially called an end-to-end performance evaluation at this point. But this should lead in the end to the development of the ground processing infrastructure, be able to process in the end these two pairs. Of course, there's also a lot to do regarding methods development. So there's also food for our PhD students for several generations now to work on improved methods, how to best process and analyze and extract information of these double pairs. I don't want to go into detail here, but just end with the good news now. So I already mentioned that the funding of the polar pair is currently already secured. This will be NASA plus ELR, Germany, as usual. As for GRACE and GRACE follow-on. But just 2 weeks ago, there was also an approval of the NGGM pair for the current phase. This means a funding of already 150, 200 million euros going into this in the upcoming 3 years, mainly to industry, which means 2 weeks ago, the train really started rolling with full speed. And our hope is that in the next ESA ministerial conference, this final funding will be secured up until phase D, meaning until the satellite is then sitting in the rocket 2032. So the chances are really very, very high that we have then 8 years from now this double pair configuration in orbit, and with this can then also provide a significant contribution also to the GGOS infrastructure in terms of ensuring continuity and ensuring improved products, and especially ensuring that we are on the path for a sustained availability of this type of observations, which are highly beneficial, of course, also for Geodesy as part of the GGOS infrastructure. Yeah, and this is the, let's say, the long-term goal, but this magic mission constellation is the first step towards this direction. Okay, thanks. Are there any questions?
I have one.
Yeah.
I take this just to get to it. Yes. You mentioned that the new mission will have increased spatial and temporal resolution. I'm wondering, with similar orbits, what gets you the increased temporal resolution?
With, sorry, with
the new mission, increase spatial and temporal resolution. The orbits are similar. So what is it that gets you, what feature of the mission gets you higher temporal resolution?
The biggest enemy currently in these gravity missions are not the instrument performances, but is temporal aliasing. Meaning we have short-term signals which we cannot capture due to the limited temporal resolution of the missions. And it's not just an increase by a factor of 2 if you have a second pair, but due to the inclined orbit, we can reduce significantly the biggest error contribution which we have currently, which is this typical striping pattern. So whenever you have really looked into GRACE data, you will see that the original data will look like this one. So very bad striping, which we have to deal with post-processing strategies. But this removes not only the striping, but also parts of the signal, especially the higher frequency signal. And by just having the inclined orbit, instead of such an arrow pattern, you get this arrow pattern already. And this brings already a lot, meaning we need a lot less post-processing, and we get intrinsically a much higher resolution by the fact that we reduce this dominant error contribution significantly. And this is really the biggest value. So we don't improve by a factor square root of 2 by this, but by a factor of 5 to 7.
Thank you.